In section 11.2, I'm going to do some numerical examples involving universal gravitation. The lecture got a little bit long, so I split this into two parts. So I'll do the second part in section 11.3. In section 11.1, I mentioned that gravity is weak, but we typically don't think of gravity being weak. We think of gravity as being the dominant force in our everyday life. But gravity is the weakest force that we know about. Just as an example of the weakness of that force, let's take the example of two 100-kilogram people standing a meter apart. With what force do they attract each other? Because the law of universal gravitation says that all objects, including people, attract all other objects like another person. So the force between two people is given by the law of universal gravitation. The value for G, as we mentioned in the last lecture, is 6.67 times 10 to the minus 11th. And then we have mass times mass. Both masses are 100 kilograms, so mass times mass gives you mass squared. And we're going to divide this by the distance between them. We've put them 1 meter apart. And so this works out to be an extremely small force, right about 7 times 10 to the negative 7th newtons. And this is right about the weight of a grain of sand. Okay, so two people, normal people, a meter apart, normal distance, attract each other with a force about the weight of a grain of sand. That's extremely weak. It's so weak that typically we do not worry about the force of attraction between everyday objects. We ignore it. It's negligible. We only really notice gravity when at least one of the objects in the pair is very, very large, like a planet or a star. And in our everyday lives, the source of that gravity is Earth. Earth has a very, very strong gravitational field. It's important that you understand that gravity is weak, but it's also important that you understand that gravity becomes rapidly weaker with the distance between the objects increasing. Newton's law says that the force of gravity between two objects is inversely proportional to the square of the distance between them. And we can use this relationship to make some predictions between the relative force between two objects. Let's say that we have two asteroids initially a kilometer apart, and they are attracting each other with a force of 100 newtons. Well, with what force do they attract each other when they're 2 kilometers apart, where the distance has doubled? So if we keep in mind that the force is inversely proportional to the radius squared, well, then we can say that the ratio of forces, force 2 over force 1, is equal to the ratio of the distances, R2 over R1, squared and inversed. And we can re-express this as R1 over R2 squared. So notice that when you take an inverse, you reverse the subscripts. And we have to reflect the fact that it is inversely proportional to R squared. And when you do this, we can put in numbers and calculate rather quickly. So F2, the original force was 100 newtons. The original distance, R1, was 1 kilometer. And the new distance is 2 kilometers. Units of kilometers are going to cancel out, and I'd like to point out that right here, that is equal to 1/4. When we double the distance, we are going 2 squared is 4, so we're going to reduce, right, 1 over the that factor, that ratio squared, which gives us 1/4. And 1/4 of 100 is 25 newtons. Okay, well, what if we go to 5 kilometers apart? So if you can reason this out like we did before, doubling the distance quarters the force. Well, what if we multiply by 5? 5 squared is 25. We are then going to reduce the force by a factor of 25. Or if we do it the long way, we can say F2 over F1, which was 100 newtons, is the original distance, 1 kilometer, over 5 kilometers squared. Inside here, we have 1/5 squared. 1/5 squared is 1/25th. And 1/25th of 100 is 4 newtons. So you should really take a second to appreciate this, that if we were to graph the force versus the distance, we would end up getting not just a regular inverse curve like that, it would drop off much more rapidly. And so as we get really far from objects, the force between them gets very small very quickly. So when we consider objects that are very far apart, we can consider the force between them to be negligible. And that's why we don't typically worry about the force of gravity from very distant stars, from galaxies that are billions of light years away. We say that those gravitational forces are so small, it's like they're zero. I'd like to briefly re-examine g, lowercase g. Up till now, we've referred to g as the acceleration of an object in free fall, and we've measured it in meters per second squared. And around Earth's surface, g has a value of 9.8 meters per second squared, and positive physics lets us round that up to 10 meters per second squared to make the math a little bit easier. But g can be looked at in another way. G can be looked at as in the force of gravity is m times g. We could rearrange this to be force over mass. And when we look at it as the ratio of the force to mass acting on an object, we can look at that as the gravitational field strength. And we would measure that in the units of force, newtons, over the units of mass, kilograms. And the gravitational field can be expressed as lowercase g, because it turns out that these are the same two things. And the gravitational field always points towards the center of mass for the source of a gravitational field. So when we're talking about a spherical object, g is always going to point towards the center of the object. And if we're occupying the surface of a spherical planet, we're going to experience that gravitational field as down. Now, in physics, the idea of a field is all over the place. And a field is just a property of space where if you put an object in that space, it feels a force. Gravity fields exert weight on objects with mass. If you continue studying physics, you'd learn about electric fields that exert electric forces on charges. And magnetic fields exert magnetic forces on moving charges. But if you remove the object, the field is still there. So g is just a property of space surrounding an object with mass. I have to take a minute to really hammer home the fact that g, gravitational acceleration, or the strength of the gravitational field, is not always 10. Up till now, we've always used a value for g of 10, but that is only true at or near Earth's surface. If you go to some other location in the universe, g will most likely not equal 10 newtons per kilogram. And we can work out an expression for g quite easily. If we take Newton's law of universal gravitation, and I'm going to substitute m1 with a lowercase m and m2 with an uppercase m to reflect that lowercase m is just some random object and uppercase m is the mass of the source of gravity, usually the mass of a planet. And I can replace the force with the random object's mass, lowercase m, times g, gravitational acceleration or gravitational field strength. And you see there's a lowercase m on both sides of the planet. Gravitational field strength does not depend on the mass of the object that's experiencing that gravitational field. That cancels out. And so we have an equation for the strength of the gravitational field or free fall acceleration at any location. It depends on the mass of the source of gravity and the distance from the center of the source of gravity. Okay, so G is probably not going to be 10 except at Earth's surface. It will have different values at different locations. So what if we go to Mars? Mars has a radius that's a little more than half of Earth's radius and a mass that's a little more than 10% of Earth's mass. So you should expect that the strength of gravity on Mars's surface is going to be less than the strength of gravity on Earth's surface. So let's work out what that should be. The gravitational field, lowercase g, is the gravitational constant, uppercase G, times uppercase M, the mass of the source of gravity, in this case it's going to be Mars, divided by the distance from the center of the source of gravity. In this case, that's the radius of Mars. And by tradition, we use an uppercase R to represent the radius of the planet. And we have a value for all three of these variables. And when we crunch the numbers, the gravitational field strength on Mars's surface is 3.7 newtons per kilogram. What if we express that as a multiple of G? Well, if I take the value for G on Mars, divide it by the value for G on Earth, I'll use 9.8, the accurate value of G. We end up getting 0.38, which is about 38% of Earth's surface gravity. Now, if gravity is weaker, you could jump higher on Mars. How much higher could you jump? Well, if we remember jumping straight up, at your peak, you would have a speed of 0. So we can take one of our old motion equations. We're going to assume that we jump straight up. The acceleration would be downward. So we'll give down the negative direction. And the acceleration would be equal to g because you'd be in free fall. But g here is not going to be 10. And then your height would be delta x. Like I said, the final speed would be 0. If I rearrange this for delta x, how high you go, we would get initial speed squared over 2g. And this tells me that the height to is inversely proportional to g. The smaller the value of g, the larger the value for your max height. So if g is only 30%, 38% of what it is on Earth, that means that we should be able to jump 1 over 0.38 times higher, which is 2.63 or 263% as high as you can on Earth.